Welcome to homework.
So now we'll work on problem 110 from chapter 6. In this problem, we're told that the two most common isotopes of uranium are 235 uranium and 238 uranium. So in part A, we're supposed to compare the number of protons, electrons, and neutrons in these two isotopes. So we can go ahead and do that here. First, we have 235 uranium and then 238 uranium. And then we can draw protons, electrons, and neutrons. So uranium, all uranium atoms will have 92 protons because that's its atomic number. Irrespective of isotope, they will all have 92 electrons, 92 protons, and if they are neutral atoms, they will all have 92 electrons to balance out the 92 protons. So the difference between these two isotopes arrives from the different number of neutrons. So if we subtract 92 from 235, we can get the number of neutrons, which is 143. And then for 238, it would be 146 neutrons. So for part B of this problem, we're told to use the periodic table in the front inside cover, or any periodic table, to write the electron configuration for a uranium atom. So if we use the periodic table only, we'll get the condensed electron configuration to be radon, followed by 7s2, 5f4. In part C, we're told to compare this answer to compare your answer to part B to the electron configuration given in figure 6.31 and explain the differences between the two. So in 6.31, we're given an electron configuration which is radon 7s2, 5f3, 6d1. And so we do see a difference here. Instead of 4 electrons being in the 5f orbital, there's one that's moving to the 6d orbital. And the reason for this is because the 6d and 5f orbitals are very close in energy. And so this means that it's easy for, and in this case even favorable, for one electron to move from the f orbital to the d orbital. In part D, we are told that 238 uranium undergoes radioactive decay to 234 Th. How many protons, electrons, and neutrons are gained or lost by 238 uranium in this process? So we can go ahead and write the values we have for protons, neutrons, and electrons that we obtained for 238 uranium from before, and those were 92 protons, 92 neutrons, and 140. And here we have 146 neutrons. And 92 electrons. For 234 Th, the protons will be 90, the electrons will be 90, and the neutrons will be 144. So this 238 uranium loses 2 each of protons, neutrons, and electrons. In part E, we're asked to examine the electron configuration for TH in figure 6.31, and are we surprised by what we find? So the electron configuration that's given is radon, followed by 7s2 6d2. So this is surprising because normally the 5f orbital will be filled before the 6d orbital. But since these two this 5f and 6d orbital are close in energy, this configuration is possible.